I'm going to start section 5.4 by just defining independence of path before we do any examples. So we saw some examples where if you had maybe z0 here and maybe z1 here, and you had several different ways of going from z0 to z1. Maybe c1 is a circular arc, maybe c2 is this piecewise linear path, and then maybe c3 you take the straight line path. We saw examples where if we had a function, the integral over c1 of f was the same as the integral over c2 of f, was the same as the integral over c3 of f. So we saw examples where that's true. And we're going to try to define when this happens in general, and then we'll state a theorem at the end. So definition, let me just say this isn't always true, but we saw examples of this. All right, so definition. Suppose that z0 and z1 are in a domain. We say a contour integral over c f of z dz, where c begins at z0 and ends at z1, I'll clarify that in a second, is independent of path. If it is the same value for any contour beginning at z0 and ending at z1. So it does not matter how you go from z0 to z1, the value is the same, which means if you're trying to compute that contour integral, you should pick the easiest possible parameterization, the easiest possible way of doing it. Sometimes that's just the straight line path, but sometimes it's a circular path. It's just whatever gives you sort of the most cancellation in f to make your life easy. In the main theorem, well, one of the main theorems is that, let's see, what color do I use for theorems? I think I use pink. Is this, well, basically you're independent of path if you're analytic. So suppose f of z is analytic in a simply connected domain. We need simply connected because when you integrate around holes, you might be analytic in the domain, but the integral around a hole is non-zero. So, and certainly if you integrate, if you do an integral over a simple closed contour, the beginning and ending are the same point. So you should get zero if this was true, but you do need simply connected. And then we'll say what happens if you have something multiply connected later. But if you're simply connected and C is any contour in D, then the integral over C, f of z dz, is independent of path. So you can take any contour you want as long as you remain in D, which is wild. So this is further saying that analytic is a very strong condition to put on a function. So complex differentiable at a point and in a neighborhood of a point. And it somehow makes everything magical, like this theorem. This theorem is magical. And it's somehow independent of path. No matter how you get there, it'll all be the same value. So this computationally is helpful because it will tell us that we can pick whatever path we like. And we'll see an example of that next.